Hi everyone, I want to continue our discussion on the Boltzmann equation, which says that entropy equals K times L and W. This is a continuation from last video. To understand the Boltzmann equation, we'll need to have a discussion about microstates, and at the end of the video, we'll do a couple of simple problems on predicting the change in entropy. Okay, the Boltzmann equation has entropy equal to K ln of W. Now, I'll remind us what entropy is. There are a couple of definitions, but the main definition is, well, for me, is a measure of disorder. The technical definition is a measure of how spread out a system's energy is. How spread out a system's energy is in space. And that actually is going to help us a lot in the discussion and the example I'm about to show. W. The key to understanding the Boltzmann equation is to understand W. W is, and again, this is just a rehash of the last video, number of energetically equivalent different ways. The English sounds, or the grammar sounds a little odd. You'll see hopefully what this means in just a bit. The molecules in a system can be arranged. It's a number, whole number. Okay. Now, let me give us the definition for microstates. And actually, before we do even microstates, there's actually something called macrostates. Oh, shoot. So this is A. Let us call this, yeah, we'll call this B now. A was a short review. B, let's talk about macrostates. A given set of conditions defines a, it's kind of a law definition, not very interesting. But when we apply it, I think we'll see the benefit of defining a macrostate versus a microstate. A given set of conditions defines a macrostate, and if those conditions are constant, energy stays constant. That is macrostate. Microstate. But the exact internal energy distribution in the example in this video, we're going to be working with gas molecules, and you're trying to visualize the kinetic energy and the potential energy of these molecules whizzing around in a defined space. So, but the exact internal energy distribution at any one instance is the microstate. Okay, digest that for a bit. Let us have two vessels that are connected by a tube. Right now they're closed off to each other. The valve is shut. And this idea of macrostate and microstate can get super complicated the more atoms and molecules you add. I'm going to have 4 gas molecules. And we're going to track them. And what are all the different permutations? And what are the relative energies? Okay, if we open up this valve, you may or you may not predict. What would you say? Is the gas going to move or is the gas going to stay? Question mark. Question mark. Now, in our example, we're going to have 2 volumes, 2 vessels basically. Vessel A and vessel B. Those are called cells. A and B vessels are cells. So right now I have 2 cells. Now, theoretically, you could have an infinite number of cells. You could subdivide the cells to get more cells. But again, it's going to get super complicated if we add more cells, add more molecules. All right. So the goal is, and I'm going to start a new piece of paper, and I suggest you to also. At the very top, we're going to define the macrostates and the microstates. In actuality, the macrostates will have 1 or more microstates, and you'll see sort of a game how we're going to sketch out each of these states. Forget about the definition, all right, for now. Let's just concentrate on diagramming what's going to happen to those 4 molecules. We have macrostate. Those 4 molecules could occur in several different arrangements. Okay, and again, entropy is, we're going to spread out those molecules and figure out how the system's energy is distributed in space. The W is how those molecules are arranged. Okay, so we are getting to this idea of the Boltzmann equation. Macrostate number 1, all 4 molecules stay on the left. I'm not going to draw the vessels every single time, so I'm just going to put a dotted line separating what? The 2 cells. 2 cells A and B. Okay. Number 2 is going to be, I think, very helpful for us to visualize, because what could happen in macrostate number 2 is maybe one of them goes to the right. The microstate is going to tell us how many different ways can this happen. How many different ways can the macrostate happen? So we are going to keep track of the actual molecules 1, 2, 3, and 4. Let me just set us up for the microstate on this side. And I kind of like how I put it. It is the ways that the macrostate can occur. All the different ways macrostate can occur. Okay. Let me draw us the rest of the macrostates though. Skip a couple of lines and then we'll do 3. 3 is 2 and 2. Don't worry that I'm drawing some of these as diagonals. It doesn't matter. It really doesn't matter. Just 2 and 2. We need to skip a couple more lines, so let's skip maybe. Yeah, let's skip that many. It looks like about 1, 2, 3 lines about. Okay, now we can have 1 on the left and 1 on the right. Oh, sorry, 3 on the right. Now you may say, well, aren't those two the same macrostates? No, we are going to use the cells, and yes, we're going to say 3 are in cell B in this case, and then 3 are in cell A in this case. And those are energetically equivalent, but those are still considered different macrostates. Literally, the molecules had to move from the initial state. Okay? And you can either move 1 to the right, or you can move 3 to the right. And then finally, what if all 4? Now, you may already know that that is so unlikely. Well, not so unlikely. But if we had maybe a billion molecules or a mole of molecules, then with all of them on one side, on the right side, once you open the valve, that is super unlikely. Very unlikely. Okay, let's go back up here. This is the game we're going to play. We are going to number these 1, 2, 3, and 4, but the only microstate that can occur that gives us the same energy as this macrostate, or the that gives us the macrostate period, is if we have 1, 2, 3, 4. Again, it doesn't matter the order. What matters is they're all on the left side. What this means is there's only one way to have this macrostate. This is the microstate. There's only one microstate to achieve this macrostate. And we're going to think of it as probability. Okay, just one. Out of all the different microstates, I don't know how many there are right now. One out of that many is the probability that we'll find all 4 molecules on side A. But for macrostate number 2, we could kick over molecule 4. So we could have 1, 2, 3 on this side and 4 on this side. Now we have to go through all the permutations. We could kick. Why would I kick out 4? We could kick. Let's go backwards. We could kick. I see what I'm doing. We could kick over 3. 1, 2, 4. And then on the other side, we have molecule 3, gas molecule 3. We could kick over 2. 1, 3, 4. And we kick over 2. And the last one is 2, 3, 4, and we kick over 1. What this means is that there are 4 possibilities, 4 microstates that give us this macrostate situation. And you could almost say, well, not almost, you could definitely say there's 4 times as greater probability that we'll have this macrostate over this macrostate. Okay? So there are 4 microstates. That's my conclusion. 2 and 2. This one will have the most. If I had to ask intuitively, what would you say is the most spread out? 1, 2, 3, 4, or 5? I think most of you will say, well, they'll balance out, and probability-wise, it'll be 50-50. And you would be right. But let's see how many exactly microstates we get. Oh, there's going to be a lot. Afraid I'm going to mess up. Just give me 1 second. Oh, okay. 1 and 2, and 3 and 4 on the right. Let me actually draw my 2 cells. There's going to be 6 of them in total, I think. Okay, 1 and 3, 2 and 4. Make sure I don't repeat. So I'm keeping, for the first row, all the ones on the left. 1 and 4, 2 and 3. Now, what can I have here now? I could have 2 and 3. We haven't had that combination yet. 1 and 4. We have 2 and 4. Yep. We can have 2 and 4 and 1 and 3. And we're missing one. 3 and 4. 3 and 4 and 1 and 2. I think those are the only combinations. So just pick two numbers randomly, like, I don't know, 2 and 4 right there. 1 and 2, 1 and 3, 1 and 4. 2 and 3, 2 and 4, and then 3 and 4. That's it. 6 microstates. Next, okay, so I'm not going to draw this because it is the same as microstate number 2, except you reverse. So I'm going to put here same microstates as macrostate 2, just flip the cells, just reverse. What that means is that there are 4 microstates for macrostate number 4. 4 microstates. And then here, there's only one way that we could have this situation occur. So there's only one microstate, just like we had for macrostate number 1. Okay, let me circle the number of microstates in total. 1 here, plus 4, plus 6, plus 4, plus 1. There are 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, 16. There are 16 microstates. When you let the gas distribute itself. Okay. All right. I mentioned at the beginning that it's important for us to know W well to be able to use the Boltzmann equation. W, in this case, there's an equation. And yeah, let me go back to the second page. W equals x to the n. What is going on there? W equals x to the n. Very simple. You know that W is in the Boltzmann equation. X is the number of cells. Now, would we get a different W if I had decided that, well, instead of having 2 cells, I could subdivide each of these cells and have 2 more on the left and 2 more on the right, so for a total of 4 cells. I'm not going to go through that exercise, but you would get the same result in terms of the entropy. Anyway, n is the number of molecules. Okay, I think that worked out because what do we have here? W equals 2 cells. Oh, I hope it works out actually. Is that the right number of cells? Yep, number of molecules. Uh-oh. Man, did that not work out? Oh, thank goodness. 2 times 2 times 2 times 2 is 16. I don't know where my head was. Thinking that it wouldn't work. 16. There are 16 microstates. Okay. All right, great. We could now say that when we have S equals K ln of W, W is the number of microstates. Microstates. By using this equation right here. Let's calculate S, but most likely this chapter's long, or this unit's long. It's going to be rare that you'll actually do a calculation. It will be more likely that maybe you'll need to be able to diagram or to figure out the number of microstates. But anyway, Boltzmann constant is 1.38 times 10 to the minus 23 joules per K, and then ln of 16 equals entropy S, okay, entropy of the system, 1.38 times 10 to the negative 23 times ln of 16. Okay. Oh, yeah, the number doesn't actually make a lot of sense because it's nothing that we would ever see in real life because there's only 4 molecules. That's why I was a little confused by the number. Normally you don't see an entropy this low, but it does. This is the real answer because again, we're only working with 4 molecules. All right. Okay. Let us go to a problem from the textbook. What's more important, instead of practicing a lot plugging in numbers to the Boltzmann constant, is literally, could you tell whether the delta S is positive or negative? And here we have the same diagrams again, the vessels with molecules in them, but also we have some processes. Know this, delta S, right, is positive if obviously entropy increases. And from our definitions at the start of the video, a measure of disorder, or you can think of it as how spread out a system's energy is in space. How spread out. The more spread out, the bigger the entropy. The more disorder, the bigger the entropy. So we could even say, disorder goes up, or distribution goes up, either way. Okay, and obviously negative would be the opposite. Disorder goes down, or the amount of distribution goes down. Dew forming. This is going to be easy. Dew forming means that you have water vapor in the air in the morning, so this is gas, and forms water droplets on the grass, liquid. Which one is more ordered? The liquid's more ordered. The gas is more disordered. So delta S is negative. You are getting more ordered. Okay, so you could either think of this as getting more order, or you can think of it as losing disorder. That, in a nutshell, is entropy. Water freezing. Liquid to solid, you're getting more ordered, so you are losing entropy. Dry ice subliming, you're going from solid to gas. I think people see disorder easier. See, we're gaining more molecules that have more freedom of movement. They're distributed even further apart. That's what you're thinking about when you gain entropy. More disorder. So this is positive. So let's go to the cartoons. You have initial state. This is S initial, and this is S final. Who has more distribution? Who has more disorder? Which one is more spread out? Those are the situations where you have a greater entropy, greater disorder. You know that eventually you'll get a 50-50 mixture. There are more microstates for this situation than this situation. there's more entropy here. So delta S is positive. Did you hear what I said? So how can we describe this? This has more disorder. This is more spread out. Okay? This has more microstates. We proved that with 4 atoms or 4 molecules. This one where it's a 50-50, we had 6 microstates. Last one, we have 3 vessels, not a big deal. If I give this on an exam, a picture like this, it'll be obvious which one is more ordered and which one is less ordered. So you see how for this to happen is going to be pretty rare, where all 3 molecules, not pretty rare, but more rare than this. There are more microstates here. So this has a larger entropy. Again, we could put here larger S, and in this case, the left side is a larger S. So the final state is a lower S. A low number minus a big number is a negative number. Delta S here is negative. Now, I know this is very abstract, the first 2 videos of this unit. We are going to be going to more concrete calculations, and we are going to see, we haven't actually seen a chemical reaction yet. We will see chemical reactions in a couple of videos, and we will be calculating change in entropy, and then going back to whether that reaction is spontaneous or non-spontaneous. So we're going to tie it all together in a couple of videos.